So I'm going to introduce this idea of independence here. It's something that we'll come back to again and again and again throughout the topic. But just to introduce it the first time, two events, so two things like being a brown dog or being a dog that can fetch sticks, for instance, are independent if one event occurring has no influence on the probability of the other event occurring. So an example of an independent event in this case might be the probability the dog likes beef-flavored treats and the probability that the dog has spots. I'm assuming here that there's no connection to the fact that if a dog has spots, it would be more likely to like beef, or if it liked beef, for instance, it would be more likely to have spots. Those two events occurring, that it likes beef or that it has spots, are totally independent of each other. They have no influence on each other. An example of events that would not be independent would be something like the probability that a dog likes to herd sheep and the probability that the dog is black and white. Okay, so the reason I'm giving that one is that, well, most border collies are black and white, and a lot of border collies like to herd sheep, so if it likes to herd sheep, it might be more likely to be black and white because it might be a border collie. I mean, there are other dogs that are included in the working class dogs, of course, that will work stock, but, you know, a large portion of those might be border collies, and so there is a potential influence there. So it's not a clear-cut independent event. It might still be if we tested it, but it is something that there could be a connection between the two. Other things like non-independence events might be that, you know, if it is raining outside, somebody will wear a raincoat. Like if it's raining, there's a higher likelihood that people are going to be wearing raincoats. And so those again would be a not independent event case. So there's a test that we have to use for independence, and you have to memorize this because it will not be given to you in the exam. And that's how it's written out as a formula, but what this means is what's the probability of A and B happening times the probability of A, or equal to the probability of A times the probability of B happening. So that first part, the P bracket A union B, that's just saying what's the probability of A and B happening together, and then we'll check to see if it's the same as the probability of A happening times the probability of B happening. So we have to test this formula. We're literally checking to see if it's going to be true or not. If it's true, we have independence, and if it's not true, if the formula is not equal on one side and equal on the other, then it's not independent. So let's take a look at an example. We're looking at investigate whether the chasing cats and liking cats are independent events. So what I might write here, just so you can see what I'm doing, is what's the probability that they chase and like cats? We're going to test to see if that's true. If it's the same as the probability that they chase times the probability that they like cats. So if we go back up to our table, the probability that they chase cats, that was 88 out of 180. And the probability that they like cats is 125 out of 180. So let's fill out that part of the equation. The probability that they chase cats was 125, or was it the other way around? Oops. Chase cats is 88, sorry. So the chase cats is 88 out of 180 times the probability that like cats. There was 125 of them that liked cats out of the 180. And now let's look for the probability that they chase and like cats. So the ones that chase and like cats, it's only that group there. There's only 58 dogs out of 180 that both chase cats and like cats because they overlap on that part of the table. So 58 out of 180 is going to be this side of the equation here. So 58 out of 180. So again, this is the one spot on the table where they both like and chase cats at the same time. This is the total that like to chase cats, and this is the total that like cats out of the 180 total each. And we're just going to plug this into a calculator and see what we get. So 58 divided by 180, you get 0.3222. And we're checking again to see if this is equal to 180, or 88 divided by 180 times 125 divided by 180. And we get 0.3395. So you can see that these two numbers are not equal to each other, so you can put a line through it because it's not equal. So you'd say not true, therefore not independent. So there might be some influence. For instance, if a dog doesn't like cats, it might be more likely to chase the cat. And we'll just do one more example on this, just to check, and we'll investigate whether the events of fetching a stick and obeying the stay command are independent. So here we're going to look at the probability of fetching and stay, and we're going to test to see if that's the same as the probability of fetch times the probability of stay. So if we go back up and look at our original table, the probability that they fetch and stay is going to be that 38. So that's the group right there that both fetches sticks and stays when asked, and that's out of 180. The other categories that we need to look for are the probability that they fetch sticks, which would be 84 total out of 180, and the probability that they stay, which is going to be the total of 52 out of 180. So those will be the numbers that we're going to put into our formula. So again, the numbers that both stay and fetch sticks was just 58 out of 180. The total probability of fetching, there is a total, oops, sorry, not 58, 38. There was a total of, I forget which was which, but one of them was 84 out of 180, and the other one was 52 out of 180. So it doesn't matter which order you write them in necessarily because they're timesing. But we're going to test again to see if this is true. So if we plug it into our calculator, we get 0.2111 for the probability that they both fetch and stay. And here, timesing those two fractions together, you get 0.1348. So again, we see that this is not true. So not independent events. And this again is a skill that you'll have to prove over and over again in the standard typically, in all sorts of different problems, so it's nice to get introduced to it. We'll go through it again and again and again. But again, if you're asked about testing independence, you need to remember this formula. What's the probability that both A and B happen? And test to see if it's the same if the probability of A happens times the probability of B happening. And again, if that's true, you have an independent event, and if it's not true, they're not independent.